In this video, I will talk about the pressure and vapor pressure. Both of them are very important properties in the fluid. So, in fact, let's start by defining what actually is pressure. So, pressure is defined as force per unit area. So it's the force over area. So it has the units of Newton per meter square, which also known as a Pascal. And in fact, this is a very small quantity because you're talking about 1 square meter area and only a 1 Newton force is applied. So it's a very, very small quantity. So usually it's defined in terms of kilopascals. And this is the definition of a pressure. But in terms of fluids, the pressure is slightly defined. I mean, it's defined differently for gases, and it's also I mean, the idea is still the same, but it's defined differently for gases and for liquids. Okay, so for gases, if you think about it, so let's just take a container. There are a lot of molecules, and those molecules actually strikes the surface of the wall or any object that's in there, and they change their direction. Okay, so there is random motion, but I mean, so most of them, I mean the average, they do collide with the wall or any object, and they are bounced back. So they have some velocity. So the change in the momentum of those molecules basically result in a force, and force divided by area basically gives you the pressure. But in case of the liquids, as I mean, we will take a look at that. But the idea with the liquid is because a lot of fluid has a lot more weight. So if I am looking at some point over here, so there's a lot of weight above this point, um, and and we can define this in terms of pressure, which is weight over the area. So if we have certain area where this weight is acting, the weight of the fluid above that point, and then the weight, which actually has the units of force, which is a force acting in this direction, so divided by the area gives us the pressure. So it's slightly defined in a different way for both of those. So this is for gases, and even for so in fact let's define the atmospheric pressure. So the atmospheric pressure, so before I actually define the atmospheric pressure, let me actually define a reference line which I'm calling as pressure absolute zero. Okay, so absolute zero or complete vacuum. So if there are no molecules and I mean in the environment, so basically they won't be colliding with the surface, and then there won't be any force. So force divided by area basically gives you a zero pressure. But as we do know, there are a lot of molecules in the atmosphere, and once those collide with some surface, they bounce back, the and they exert some force, and we define force by area as the atmospheric pressure. So those are and this quantity, which is the atmospheric pressure, is equals to 101.325 kilopascal. The other thing is, and we will talk about that in a minute. But the as we get closer to the I mean, if you have a mountain, okay, so if you have a mountain, so somewhere over here, you will notice that because of the gravity of the Earth, okay, so more molecules are pushed closer to the Earth's surface, okay, when it's close to the sea level. And as we go higher and higher in the altitude, we will notice that the pressure actually starts decreasing. So higher the altitude, the pressure actually starts decreasing, and a consequence of that is also you have less molecules there, so the density of the air actually also reduces. So the pressure reduces, the density reduces, but as you get closer to the sea level, you will notice that you have higher atmospheric pressure, and the atmospheric pressure the value is taken to be 1 or 1.325, but as you will go higher up in the mountains or even higher up in space, you will notice that the pressure actually keeps on decreasing. Okay, so this is defined as the atmospheric pressure, and anytime we go above the atmospheric pressure by adding more molecules in the container, or even so more molecules in a container, we basically go above the atmospheric pressure, and that pressure is actually known as the gauge pressure. So if you know molecules, we go to the atmospheric pressure, and anything above the atmospheric pressure, this is known as the gauge pressure. And most of the devices, they actually measure the gauge pressure, and we will talk about that, but some of them actually they do also look at the absolute pressure or the atmospheric pressure. So at this point I can say that this is my absolute pressure, which is equals to P atmospheric plus P gauge. And the opposite of that is we are at the atmospheric pressure, but now I am going to remove some molecules, okay, or if I make the air less dense, to take some molecules out of from there. So now we are basically going towards the vacuum. So this is the P vacuum. I can either write it this way. So this was absolute vacuum, this is some vacuum, and this over here, if I'm writing in terms of absolute, so this becomes P atmospheric minus the P gauge or the P vacuum. So okay, so this I can write this as P vacuum or something, so because we have removed some of the molecules from here. Okay, so this is an important definition in terms of the atmospheric pressure and so on. So let's actually look at some of the consequences, as some of the observations you probably would have made. So in this, I'm just defining the P atmospheric, which is the standard that they come up with, that this is the atmospheric pressure. And as I mentioned over here, you will have the atmospheric pressure when you are close to the sea level, but as you go higher up in the elevation, the pressure decreases, and so is the density of the air. So the density of the air also decreases. So some of the things you probably would have noticed, at higher elevations we tire quickly because it's a low pressure, you have low oxygen. The power of the car also reduces at high elevations, and that's why you would need turbochargers to basically compress the air so that you have complete combustion and more power. Air is less dense, again at higher elevation, so lift force is also less. That is why there are longer runways are made at higher elevations. So now the idea is, if you have a airplane wing, so the airplane, the way it works is that you have this air coming in, and then it basically turn in the other direction, and the change. So as the direction is turned, the third law says that you will basically be able to create a lift. But now you have the density of the air is less, so the mass flow rate that's coming in and it's moving, it is actually less. So you would require longer runways to basically create the same amount of lift. So, and even the same idea also is true for the drag. So for if the air is less dense, so you will have less drag, and that's why more home runs are hit in Colorado compared to anywhere else. And also the water boils at temperatures below 100 degrees Celsius. Okay, and that's one of the consequences of low pressure, and we will talk about that, and the vapor pressure also is involved in there. Okay, so the next thing is, as I mentioned about this air, um, the pressure varies with height for the cases of liquids. So I can write this as liquids, and let me actually take one element of the liquid, and as I mentioned that the pressure will change. So we have a pressure P1 over here, and this is pressure P2, and let's say that this is completely filled with liquid. So this is everywhere is liquid, and I just took one element out from here, and as you will notice, there is some height h1. So there is some liquid on top of this, so that's why the weight divided by the area gives us the pressure. But on this one you have more liquid sitting on top, so that's why you will have more pressure in this direction. And the thing with the pressure is it always acts normal to the surfaces. So if you have a surface like this, the pressure will be normal this way. If you have a surface like this, a pressure will be normal this way. Surface like this, so pressure is always normal to the surface. So in this case, that's where it's normal to. And this distance is delta x, this distance is delta z, and I have defined this fluid element over here which also has this delta y. So this is our surface area, this one and this one, where the force or the pressure is acting. So in this case, as we have a higher, more liquid rest on this layer, so we can see that P2 is greater than P1. And if I do the force balance in the Z, P2 delta x delta y, that on this area the pressure is acting, minus P1 delta x delta y is equals to, and anytime you will have a pressure difference, the fluid will start moving. Okay, so that's how actually the fluid moves in the pipe. You will have a higher pressure here, you will have a lower pressure here, and that's why the fluid is moving. If there is no pressure difference, then the fluid will actually be stationary. So if the pressure P2 is higher than pressure P1, then the fluid element should actually move this in this way, but it does not, because it's stationary fluid, because the weight has to be balanced by those pressure differences. So either I can write it in terms of that because I'm doing the force balance, or I can simply make them equals to W, which is the weight. So if I'm looking at the forces, so P2 delta x delta y minus P1 minus W is equals to 0, because I'm taking this side to be positive, this is negative. So and then W can also be written as delta x delta y minus P1 delta x delta y minus rho g delta x delta y delta z, which actually is the volume. And now I'm going to divide everything by delta x delta y, so minus P1 minus P2 is equals to rho g delta z, and where rho g is gamma delta z. So this gives me the change in the pressure as gamma times delta z. And one thing I can notice is, because density, I can say that the fluid is constant, acceleration due to gravity is also constant. So in this case it's a liquid, so I can treat this to be incompressible, and if it's incompressible, then the density is constant, and then the acceleration due to gravity is also constant. So the only way the pressure is changing from point inside the liquid is as we change our depth, and it actually is changing linearly. So the pressure, how it changes inside the liquid, it changes linearly. Okay, so it's a linear relationship, that this is how the pressure is increasing for the case of a liquid. But I just want to make a note here, and this is for gases. And as I also already pointed that out to you, the pressure in a tank, pressure in a tank containing gas can be considered uniform. Since weight of the gas is too small, weight of gas is too small to make any significant change, to make any significant change. I'm talking about in terms of containers, but some people actually also look at the atmospheric pressure in terms of, like when I mentioned to you that it is the as we get closer to the sea level, there is more pull from the gravity, and you have more dense molecules, and they are, there are a lot more molecules, and when they strike you, you have a higher pressure, which actually is the atmospheric pressure. But some people actually also consider, like for example, for a container, you have certain number of molecules, so for that's okay, you don't have to consider the height of the air column or the gas column. but some people actually take the atmospheric pressure, also the height of the fluid column that's above you. I mean, that can be in terms of, um, I mean, that's a very, very long distance in terms of um, kilometers. So, but in reality, you don't really have anything, a container which can be that long, so you can pretty much neglect it. And anytime somebody says the container pressure is this much, so that's the pressure that you have to take into account. Because for the cases of the liquid, um, the pressure will change as you will go inside the liquid. So that's the difference between the liquid and the gas. Alright, so continue with our discussion of the pressure inside a liquid. Um, Now I'm going to look at the height. Okay, so I mean we looked at an incompressible fluid, but if density of liquid is changing, okay, so I can write this as dP, which is the change in the pressure P2 minus P1, is equals to 1 to 2 rho g dz, and here is my coordinate system. This is x, this is z, and now I'm calling this point to be 1, this point to be 2, okay, and this is the height difference. And if I take and I'm gonna put a minus sign there because it's gonna be, this is a higher quantity than this one, so P2 minus P1 is equals to rho g dz, where dz is equals to z2 minus z1. Um, and this minus sign is basically to balance this equation, but if I'm taking the absolute quantity in terms of h or just the positive number, then I don't have to worry about this negative sign. But just to make it consistent, I'm going to so that in the end it basically comes out to be a positive quantity. So P2 minus P1 is equals to um, rho g z2 minus z1. Okay, so because it goes from 1 to 2, so that's what it will be. And I am taking this out. I mean if I take the density constant, then you can take it out, otherwise you will have to integrate how the density is changing with the height. So I'm just writing the simple form. So P2 minus P1 is same as rho gh. Okay, as that's what we actually looked at before. So P2 minus P1 is rho gh. So it only depends on the height of the liquid, and I mean the pressure difference only depends on the height of the liquid. And this is also known as a Pascal's paradox. And let me define what exactly that means. So if you notice, the pressure difference only is a measure of the height variation. So let's suppose if I have a container that looks something like this. I take another container that looks something like this, and I take another container which actually looks something like this. Okay, so if they all have the same level of liquid in them, this is a free surface, so that's the same liquid. So the pressure at all of these points, if they are at the same altitude, so they will, in the same liquid, so this pressure P1 has to be same as this pressure P2, and this has to be same as P3, because the pressure, which only depends on P2, I mean, so if in this case P2 minus P, or like just changes by the height itself and nothing else. And if all the heights are the same, then basically the pressures have to be same also. So this is also known as the Pascal's paradox, because it's not so obvious, because now you have more um, water resting on in here, but the pressure has to be equal. Okay, so and as we derive that, and the next thing I'm going to look at is the hydrostatic pressure. Okay, so I mean just what we were looking at, but I'm now looking at the hydrostatic pressure at point 1, which is simply the atmospheric pressure which is acting on the fluid, plus rho gh. So rho is the rho of the fluid, acceleration due to gravity, and h, height of the fluid column from here to here. And if I have multiple fluids, oil, water, mercury, then I can look at the pressure P1, which is this point, 2, 3, and 4. So the pressure P1 is simply P atmospheric, pressure P2 is simply P1 plus rho of the oil times G H1. If this distance is H1, I can take this distance to be H2 and this distance to be H3. And then I have this P3 is equals to P2 plus rho of water GH2, and I also have P4, which is P3 plus gamma of mercury GH3. And what we do know that the density of oil actually is less than the density of water, and the density of water is less than the density of mercury. They are immiscible, they don't mix, so that's how they will rest on each other. Okay, so the next thing I'm going to talk about is as the pressure in the liquid only changes with the height. So as a consequence of that, a consequence of the pressure in the fluid remaining constant in horizontal direction is that the pressure applied to a confined fluid increases the pressure throughout by same amount. Okay, so so in a confined fluid, the pressure will actually change by the same amount. So what exactly that means? So there are some applications associated with that. That the pressure, so in fact, a hydraulic press, or in fact hydraulic jacks are also an application of this. So let me define this first. So let me draw a picture. So let's suppose you go to a hydraulic jacks, and even so this one is a lift, so hydraulic lift. But there are a lot of applications based on that. So the pressure applied to a confined fluid increases the pressure throughout by the same amount. So if this is a confined fluid, you have a piston over here, you have a piston over here, and I apply some force here, and because the pressure is force per unit area, so if I apply force P1, so P1 is equals to F1 over A1, then this will be, so this pressure will actually be experienced by this piston over here, so which will be same as P2. So P1 is same as P2, and now and P2 is equals to F2 over A2. So what this tells me, that if I have F1 over A1 is equals to F2 over A2, so I can use this mechanical advantage by applying a smaller force at a smaller area. I can get a much bigger force at a much bigger area, and we have these two relations, and I can find out what this F2 would be based on F1 A2 over A1. And if I give some numbers, so let's suppose if I give F1 to be 10 newtons, A1 to be 0.1 meters square, I can give area A to be 1 meter square. So what this F2 comes out to be is 100 newtons. So which in fact is a much greater force compared to the amount of force that we are putting in at F1. But at the same time, I just want to mention that it's not that you're applying a much smaller force and you're getting a much bigger force here. The amount of distance that you will have to travel to basically lift it by a small amount, so you will basically have to move it 10 times more, and then you can only move this by 0.1. If you are moving this by 1 meter, then you're only moving this by 0.1 meter. So in other words, the amount of work that you're doing is the same. It's just that you are getting a larger force to a much smaller distance. So it's not that you are violating any law over here, but the distance that you're traveling in this one is much more. Okay, another example is of a hydraulic brake, and for the Pascal's law. So the way the hydraulic brake actually works is you have a master cylinder over here. Once you press on the brake, this piston actually moves in this direction and it squeezes the fluid into these in this compartment, and this fluid actually being pushed into those wheel cylinder pistons. So initially they are this position, but as you apply brakes, so the fluid is pushed in and they open up. Okay, so they open up, and let me show you another picture. So once these um, pistons actually open up, so wheel cylinder pistons open up, so they have those brake shoe connected to them. So the brake shoes actually um, open up outside, and then they basically get connected to the rim of the wheel, and they stop it. And anytime you release your pedal, so there is a spring, so the spring wants to bring this back, but the fluid was exerting the force in this direction. The spring wants to bring it back. So as soon as you release your brake pedal, so the spring pushes it back, and the fluid back again goes back to the master cylinder, and then the wheel starts to move again. So this is how the a hydraulic brake works actually. Okay, so we actually talked about the atmospheric pressure and everything, but we haven't talked about how actually we measure that. And one of the primitive device and is in fact sometimes still used today is called a barometer. Okay, so this is how they start measuring the atmospheric pressure. Okay, so we can measure the atmospheric pressure, and the way this goes is, so let's suppose we take a um, like some container filled with and in this case it could be any liquid, but I'm choosing that to be mercury. And the only reason I'm choosing that to be mercury is because mercury has a very high specific weight, and it also has a very low vapor pressure. But for now I'm just, because it's very heavy fluid, so it's not going to lift up as much, and I will just mention that about water. But let me do this, demonstrate this experiment, what I want to do. So you have this mercury filled in this container. Then you take a tube, like a test tube over here. So you insert this in this liquid mercury, and make sure it's completely in, and there's no air bubbles in it. And then you basically um, tilt it to a vertical position. Okay, so you tilt this to a vertical position. So this is how the test tube actually looks like now. So what happens is, because you have this atmospheric air which is trying to push this mercury, and of course atmospheric pressure is everywhere, so it is trying to push this mercury down, and as a consequence of that, um, this, I mean, it will experience some atmospheric pressure over here. I mean, it's because this thing is trying to pull in this direction. I push it in this direction, so for the same liquid layer level, the pressure will be in this direction. But at the same time, because this thing was completely filled with mercury, but as you made it vertical, the some of the fluid will seep out from this, and you will be left. I mean, so somewhere over here, this is where the mercury is left, and this area now is completely vacuum. Okay, so this is completely vacuum, because even though more fluid wanted to push down because of the weight, but then the atmospheric pressure was pushing some of the fluid up, because you have a lower pressure here, you have a higher pressure air, so the fluid wants to move in this direction, but then again the weight is opposing that motion. So after a while they become steady, and then you will notice that you will have some height of the fluid column. And we will do the force balance on this. So I will take it out over here. Okay, so we'll take this out over here. So on this side we have the atmospheric pressure. On this side I have the P vacuum, which actually is 0, and then I have the height of this mercury column. and I will do the force balance. So the force balance will be P atmospheric times the cross-sectional area over here minus the weight of the mercury column, with W is equals to 0, so both are forces. So P atmospheric minus times the area minus M, because M times G, so M I'm gonna write it as rho Vg equals to 0, and then this V, which is the volume, can also be written as um, rho AH times G is equals to 0, and I will notice that A cancels out, and this P atmospheric can be written now as rho GH. So if I know the height of the mercury column, which is this height, I multiply that with the acceleration due to gravity and the density of the fluid, I can find the P atmospheric. And the reason I use the mercury, because mercury has a very high density, and in fact I'm sure you must have, for the atmospheric pressure, most of the time it's expressed in terms of the height of the mercury column, and the atmospheric pressure usually is defined as 760 millimeters of Hg. So the 760 millimeter of Hg defines the atmospheric pressure of the mercury. The other thing is, if we use water instead of mercury, then this distance will actually be somewhere around 10 meters. So I can use water, so 10 meters of water will define the atmospheric pressure. So that's why we tend to not use water to find the atmospheric pressure, but in fact we use mercury. Okay, so another device which is used to measure pressure is called manometer. Okay, so it is a device to uh, it is a device used to measure pressure of a liquid or a gas, and this is how a manometer looks like. You have a pressure P1 on this container, then this is some fluid over here. I'm taking that to be, right now it's just any fluid, and the way we measure this pressure, we basically start out with P1, and if this is a gas, I don't have to worry about um, the weight of the gas which is acting on this fluid. But if it's a liquid, which actually I will do an example, then we have to worry about, okay, how deep that liquid is. So, but right now I'm just saying that this is a gas, so we don't have to worry about the weight of the gas. So P1, and anytime the fluid actually goes down, we basically add that distance. Okay, and then anytime the fluid goes up, we basically make it, uh, we subtract it. I can use any reference line to do the force balance, or like the height of the mercury column. I can either use this line, I can choose this line, or in fact I can choose this line over here. Okay, so this line, because it's the same fluid, so the pressure that's being exerted over here will be same as what's being experienced over here. So because it's the same fluid, so I can either make this line as my reference or this line as my reference. So in the later examples I will make, where the fluid is changing its direction, I will make, the same level of liquid, I will make that as a reference. But in this problem I will make this as my reference line, and I don't have the distance, but I'm just going to call this A and this also as A, because they are the same height. So now P1, which is in a gas, I don't have to worry about, and in fact there is no height over there, but if there is some height, I will have to add the specific weight of the fluid. So as we go down in the fluid, so I will have to say plus gamma times A. Then we go up, minus gamma times A minus gamma times H, and that is equals to the atmospheric pressure. Or I can actually make it minus equals to the atmospheric pressure. And if you notice, gamma times A cancels out with the gamma times A, so we are left with P1 is equals to P atmospheric plus gamma times H. Okay, so the pressure, this one gives me the absolute pressure, but I can write this in terms of the gauge pressure, which simply will be gamma times H, and in that case this is equals to 0 because I'm looking at the gauge pressure. So the atmospheric pressure, I can write this to be as a gauge pressure. And in a similar way, I can do the force balance on this height of the column of the fluid. So you have the atmospheric pressure acting this way, you have the pressure P1 which flows through, I mean, if that is the pressure acting P1 over here, it has to be same what's acting over here. So P1, P1, and then the height of the fluid column. And I can do the force balance, which is P1 times A plus, actually minus W minus P atmospheric times A is equals to 0. And I can also write this in terms of P1 times A minus M rho AH minus P atmospheric is equals to 0, and times A, so A cancels out, and P1 is equals to P atmospheric plus, actually it should be rho G, yeah, because I have to convert that, so it will be rho GH, which is the same expression as we got here earlier. Okay, so this is also known as the pressure, okay, the height of the, I think is the pressure head. So anytime somebody gives you this number, the height, that will be the height of the mercury column, and they have to specify if they are using some other liquid. So then you will just multiply that with the specific weight of that fluid, and it will tell you the specific, it will tell you the pressure. And in fact, most of the time when you go and get your blood pressure checked, you will notice that the good blood pressure actually is 120 by 80. So 120 millimeter of mercury and 80 millimeter of mercury. So the 120, you have to multiply that with rho times G to basically get your gauge pressure. So this is how much the pressure the heart is pumping the blood through the veins. Actually, I'm running out of time in this lecture, but I will continue with the manometer and some other devices, how you will measure pressure, and also the vapor pressure. So that will be for the next video.